Welcome back, and in this video we're going to be looking at the addition of a molecule to an unsymmetrical alkene. So I'm just going to go through that in a little bit more detail before we look at your notes. So I'm going to be looking at the electrophilic addition reaction of hydrogen bromide to propene. Now propene is an unsymmetrical alkene. In other words, the carbon, there's not a line of symmetry through this carbon-carbon double bond. So we start in the same way as we would for any mechanism, for any alkene. We're going to draw our hydrogen bromide. Our hydrogen has the delta positive and our bromide has the delta negative. The electrons come from the bond to the hydrogen and from the bond to the bromide. That's the same as normal. But now there's a little bit of a problem because there's two possible intermediates, because either that hydrogen will go on the first carbon, leaving the second carbon with the positive charge. So that would be what we call a secondary carbocation. Or you could break it so that the hydrogen goes on this middle carbon and the positive charge goes on this first carbon, and that is what we call a primary carbocation. Then the next stage would be as normal. We've got our Br negative with its lone pair of electrons, which would bond in here, and our bromine, again, lone pair of electrons, negative charge, which would bond in here. So from this we'll get two possible products. We'll get 2 bromopropane and we're going to get 1 bromopropane. And actually we're going to get a mix of both of these, but this is what we call the major product because there's going to be a lot more of it. This is what we call the minor product because there's less of it. We need to understand why we end up with more 2 bromopropane than we do 1 bromopropane. Now, both of the halogenalkanes, both 1 bromo and 2 bromo, are equally as stable as each other. So the reason we end up with more 2 bromo than 1 bromo comes back to this step. It comes back to the stability of the carbocations. So let's look at these carbocations in a little bit more detail. This is what we call a primary carbocation. The reason it's called a primary carbocation is it has one R group here, one carbon group attached to it, and 2 hydrogens. So that makes it a primary. This is a secondary carbocation because it has 2 R groups attached to the carbon with positive charge and just 1 hydrogen. Now, the secondary carbocation is more stable, so it takes less energy to form it than the primary. And the reason for this is what we call the inductive effect. Now, carbon is sitting there with a positive charge on it, and that's making this carbon group very unstable. So what the 2 methyl groups can do, either side of it, is donate a small amount of their own electrons. So they will donate electrons, small amounts anyway, to stabilize that positive charge. Whereas the primary, hydrogens can't do this. They can't add electrons onto the carbon, so they've only got 1 group which is able to donate electrons weakly. And this explains why more 2 bromopropane is formed compared to 1 bromopropane, because this intermediate carbocation is more stable. It takes less energy to form it compared to this primary carbocation. So this last one here, this is a tertiary carbocation because it has 3 R groups, all of which can weakly donate electrons, electron donating, which will stabilize that carbon even more. So the tertiary carbocations are the most stable of the carbocations. So tertiary, more stable than secondary, secondary, more stable than primary. So we're now back in your notes and we're on page 10, and we're just going to fill this in with what we now know about the reactions of unsymmetrical alkenes. So propene and butanene are both unsymmetrical, because if you draw a dotted line through the middle of the double bond, you can see that the two bits either side of that dotted line are not symmetrical. So these are unsymmetrical alkenes. However, if I did that with but2ene, you would see that these two groups are the same. So if you think about a mirror going down here, you've got mirror images each side. They are symmetrical. Works the same whether you've got E or Z, because remember you're replacing this double bond with a single bond, and therefore you're freeing up the rotation. It will also work with cyclic alkenes as long as you've got the same going both ways, as long as it is symmetrical about that point. But these two are unsymmetrical. So remember, when we add hydrogen bromide to our propene, we get these two products, 2 bromopropane and 1 bromopropane. This is my major product, this is my minor product. We do get some 1 bromopropane, just not as much as we get of the 2 bromopropane. And this is down to this stability of the carbocation. So in this case, the 2 bromopropane, the positive charge goes on that second carbon, and the hydrogen is added to the first carbon. So there's my additional hydrogen, there's my bromine. And this carbocation is more stable than the primary carbocation, because in the primary carbocation you only have 1 carbon group which can weakly donate electrons. So those are my intermediates, the secondary carbocation and the primary carbocation. We say these methyl groups or these alkyl groups are weakly electron donating, so they can loan, if you like, that positive carbon a little bit of their own electrons, which is going to make it far more stable. Because it's more stable, it's more likely to form. If it's more likely to form, it's more likely to be part of the product. So the least stable is going to be the primary, and the most stable is going to be the tertiary carbocation. So you need to be aware of that, and you need to be able to determine which is the most stable. Do remember, however, that this stability has nothing to do with the final product. 2 bromopropane and 1 bromopropane are equally as stable as each other. It's not down to the product, it's down to the intermediate carbocation, which determines which is the major and which is the minor product. So the last reaction we're going to look at is bromine water. Now don't get this muddled up with bromine dissolved in an inert solvent like cyclohexane or hexane. If bromine is dissolved in an inert solvent, you will just get Br2 and you'll just do the normal electrophilic addition mechanism. But when you've got bromine water, the bromine liquid can actually react with the water to form hydrogen bromide, but also OHBr. So there are 2 possible reactions, as 2 negative ions can add onto the carbocation intermediate. So we say bromine water contains a mixture of BrOH and BrBr. But do remember, if it's an inert solvent, you will only get this one. You won't get any of this species. You do need to be able to work out the product and the mechanism given any binary compound. And this is a binary compound. You'll look at this in more detail when we look at electronegativities later on this year. But for the moment, we need to understand that oxygen is better at gaining electrons from the bond than bromine. So the bromine in this case is delta positive, and the OH group is the delta negative group. So we get this product, and this is based on an ethanol molecule. The OH group takes priority. So it's F, 2 carbons, and no carbon-carbon double bond, ol, to show it's an OH group. Now, because this carbon takes priority, this is carbon number 1, which makes this carbon number 2. So this is 2-bromoethanol. And the other product is my 1,2-dibromoethane, which we've seen before. So with bromine, water and propene, remember propene is an unsymmetrical alkene, there are 3 possible products. So the 3 possible products are going to be my 1-bromopropan-2-ol, where the OH group goes on the second carbon, 2-bromopropan-1-ol, where the OH group goes on the first carbon, and obviously my 1,2-dibromopropane. Now we need to work out which of these 2 alcohols is going to be the major product, and to do that we need to look at the carbocation intermediates. So we have our propene molecule, and we're going to be bringing up the OH-Br molecule to be attracted to that double bond. Now it's important that you get the right end pointing towards the double bond. In this case, it's going to be the Br that's pointing towards the double bond, and the OH group which is away from it. The reason for that is in this case, remember, this oxygen here is more electronegative than this bromine. It's going to pull more of the electrons onto itself. So this end is my delta negative. This end this time is my delta positive. So that's going to pull the electrons from this bond onto this Br group, pushing the electrons from the bond onto this OH group. So this is where we get our 2 intermediate carbocations. So here are my 2 intermediate carbocations. This one is a primary carbocation and this one is a secondary carbocation, because this has 2 groups which can weakly electron donate. This one only has 1 group which can weakly electron donate. So this is going to be the more stable carbocation. So the product that's formed from this carbocation is going to be the major product. So again, it's the lone pair on the OH group, on the hydroxide ion, which is going to donate into this positively charged carbocation, and the same here. So in this case, I'm going to end up with my 1-bromopropan-2-ol. In this case, I'm going to end up with 2-bromopropan-1-ol. And it's this which is going to be the major product. So my major product is here 1-bromopropan-2-ol, because it comes from this more stable secondary carbocation. So this is my major product. And it comes back to this stability of the carbocation. So this is the more stable carbocation, so it's more likely to be formed, and therefore you get more of this product, 1-bromopropan-2-ol. So that finishes this video, just looking at the unsymmetrical alkenes and their electrophilic addition mechanisms. In the next video, we're going to be going on and looking at the last few reactions of the alkenes, and we're going to start looking at polymers. So until then, take care, stay safe, bye bye.